Looking at these limits, we want to first of all establish if the graph is continuous or discontinuous, and then be able to write a limit argument for the discontinuity or continuity. And basically for continuity, it's that the limit must exist at that point from both sides, and the value of the function at that point must be the same as the limit. So let's take a look at x equals -8. This is a removable discontinuity. You don't really, for AP calculus, you don't need to know the terms, but this is called a removable discontinuity. So first of all, it is discontinuous, and we want to give a limit argument. Okay? And so our limit argument is going to look like this. We're going to say that the limit as x approaches -8 of f of x is equal to -6, which is not equal to f of -8, which in this case f of -8 is equal to -3. So these are not equivalent, therefore it is discontinuous. So I'll just highlight that in a different color. Okay, so these are not equivalent, therefore discontinuous. Okay, so although the limit exists, the point does not exist at the limit. At x equals 6, it is discontinuous. Okay, so again, we first have to establish that it is discontinuous. We can say that it's discontinuous because the limit as x approaches 6 from the negative side is not equal to the limit as x approaches 6 from the positive side. Okay, because it's not equal, we know we can make the conclusion then it is discontinuous. Okay, so this one was different in that the limit did exist. This one doesn't even pass that first test of even having a limit. At x equals 10, we know that this is continuous. Okay, so we know that the limit at x goes to 10 from both sides is equal to 0. The value of f of x at x equals 10 is also 0. Okay, if the two-sided limit exists and the function exists at the limit, it is continuous. Okay, so this is continuous. This is a test for continuity. Okay, so the function must exist at that point, and the limit must be equivalent to the function at that point. For Newton's quotient, we only use Newton's quotient when we're asked to, and for Newton's quotient, we just basically want the limit form of the derivative. So the change in y over the change in x, or f prime, is going to be equal to y1 minus y2 over x1 minus x2. And this always simplifies to h. And to get an instantaneous slope, we need to make this into a limit. Okay, so then we end up with the limit as h approaches 0. And as h approaches 0, I end up with 0 divided by 0, so I have to simplify this to be able to evaluate it. To algebraically simplify this, there are basically 3 types: the 1 over x type, the polynomial type, and this square root type. For the square root type, we need to multiply by a conjugate. Okay, and what this will do, it will generate a square minus a square, which will then free up the h from the square root. Okay, so I'm going to multiply both sides by that conjugate, or sorry, both the top and bottom by that conjugate. Okay, so when I do that, I'm going to end up with the limit as h approaches 0. This becomes a difference of squares, so I end up with x plus h plus 2 square root squared minus x plus 2 square root squared, which gets rid of the square root. Okay, that frees up my h. I end up in the denominator, I can't multiply this out, so I'm just going to keep it the same. X plus h plus 2 plus square root of x plus 2. So I have my factor of h that I want to get rid of, and notice I have things canceling out here. X cancels with minus x, 2 cancels with minus 2. I end up with h divided by h. There's how I'm going to free up my, get rid of that 0 divided by 0. So I end up with limit as h goes to 0. Okay, we end up with 1 over square root x plus h plus 2 plus square root of x plus 2. So now that I've gotten rid of the 0 divided by 0, I can then evaluate this limit. I can plug h as 0. I end up with square root of x plus 2 plus square root x plus 2. Well, that simplifies to 1 over 2 square root x plus 2. And so there's the derivative of square root x plus 2.